Hi everybody. So today's talk is going to be given by Luigi. He's going to talk about the role of optimization to analyze some statistical properties of some function. That's far I understood. So enjoy.
So thanks, Veronica. So as Veronica was saying, the question that we're going to try to give an answer to is how optimization in machine learning, and especially in large-scale machine learning, influence the statistical properties of the function that I want to learn. This means what can I say about how good my function is going to be on future data, how good my function is going to generalize based on the type of optimization that I want to choose. So usually machine learning, when you want to study the statistical properties of a function, what you do is you build a model. So you say, okay, I have a training set. Based on this training set, I'm going to decide to solve this problem with neural networks, SVMs, or whatever model I want to use. And if I want to study the statistical properties of the function that I'm going to learn, what I'm gonna look at is at an error, which is the test error of this f hat star, which is the exact solution of my empirical problem. So I have my training set, and I use the training point to train my model. And if I know that I can have an exact solution to the empirical problem, this is f hat star. So if I want to study the statistical properties of the function that I'm going to learn, I have to look at the distance between the test error of this function here and the best possible function that I can learn. So, of course, here I'm not telling you how I'm going to solve the empirical problem. So after the statistical machine learning people studies how to control this quantity here, then the optimization guy enters the room and says, okay, so now I know that I have to solve an empirical problem. How am I going to solve it? And usually lots of choices can be made, especially nowadays that we have large amount of data. So we have to deal with large-scale problems. So we have to start thinking about, okay, so I'm going to use an iterative method, I'm going to use a gradient descent, but actually I'm going to use a stochastic gradient descent. But then because I don't have enough memory, I'm going to use some approximation techniques in order to actually optimize better my function, and this kind of thing. So what the optimizer does is studying the distance between the training error of the function ft, which is the tth iteration of any iterative algorithm. You can think about gradient descent, and the training error of the exact solution of the problem. So the optimization guy studies this distance here and says, okay, so what I want is to be able to control this quantity in a way that this distance here is small. So, as I told you at the beginning, the question is, okay, but when I study how good my function is on future data, usually I take into account that I have for free f star. But in practice, I never recover the exact f star, but I have ft. So what can I say about the choices that I make in my optimization process that's going to tell me something about the statistical properties of this function? So now we can start to understand better what I mean with test error, training error, and all this kind of thing. So if we start trying to formulate the problem, what I can say is that usually in statistical machine learning, the important thing that I need to know is that I have points which are generated by a probability distribution. And to simplify things, let's consider that I want to learn linear functions. And ideally, what I would like is to minimize what I was calling before test error, which is this quantity here, which is the distance between the function that I can learn and the labels over all possible points that I can generate by my probability distribution row. Unfortunately, I cannot generate points as my pleasure because the probability row is unknown, but I have just a set of endpoints. So these are my training points. So this problem cannot be directly solved, but can be studied theoretically. And this is where statistical machine learning people studies how to control this quantity here. So what I have in practice is I have to solve an empirical problem. So with the data that I have, I can somehow change this integral here into a sum over the points that I have. And then what I have to do is I have to say, okay, but remember that I don't want to solve exactly an empirical problem. I want to solve a more general problem. So I have to regularize my solution. I have to allow myself to don't trust too much the data that I have. And so you usually add a regularization term to my empirical problem. Now, statistical machine learning people says that this quantity here, which is exactly what, sorry for the notation, what here I called test of f star minus the minimum of test f. This quantity here can be controlled by, let's say, with under the least amount of assumption, a quantity that decreases with the number of points that I have, and usually the best rate that I can recover is 1 over square root of n. Because you start saying that you have this W lambda, which is the exact solution of my empirical problem. So then, as I told you before, usually people cannot have the exact immediate solution of this problem here, but use optimization. So the optimization guy says, okay, I'm going to solve this problem here with gradient descent. So what I'm going to do is I'm going to update my solution WT with an iterative method that takes into account the gradients of the previous problem. And now, what the optimization guy says is that the Tth iteration of the algorithm converges to the exact solution at a certain rate. But again, as I told you before, here I don't have anything about generalization properties. So the problem arises especially because usually we don't use gradient descent. Large amount of data, few computational power, or distributed computational power. So what I have to do is to start taking into account the fact that maybe I'm not going to work with gradients, but actually with stochastic gradients. Probably I'm going to use mini batching to adapt to the computational power that I have. So think about you have a GPUs. So what you want is, instead of taking random batches of points, you want the batch that perfectly fit in your GPU so that you use efficiently all your resources. Probably you don't have enough memory, so you don't have enough RAM. So you're going to use sketching techniques that I'm going to tell you later what they are, in order to use less memory as possible, or not less memory as possible, but as much as you can afford to. And all these ingredients here are choices that we make, and for which we don't know anything about what's going to be their effect on the generalization properties of the function that I'm learning. So in this work, what I'm gonna try to show you is, in particular, how the iteration, so for how long I have to run my iterative algorithm, how the stochastic gradients, how the step size, how the mini-batch, and how the sketchings, all of these influence my solution. So let's start understanding what I meant before with sketching. So so imagine that you want to learn a non-linear function f. So usually what you do is that you parameterize the nonlinearities in this way. You say my nonlinear function f is a weighted sum, and where the weights are these w, of some nonlinear features. What I mean by that is that you take each one of your training point x and you put it through a feature map phi of m, and what it does is that it takes your point and map it into another space, in particular into Rm. So I'm going to have m features which are nonlinear. What I mean by that, is that each one of these random features are going to be the inner product between the point x and a random vector si that goes from 1 to m, and then the result is going to be used as input to any nonlinear function sigma. And the S1, Sm are random vectors that you can choose as you want, and as well sigma is a nonlinear function that you can choose as you want. So this can be a cosine function, a ReLU function, or whatever. Why do we like this? Well, because this is a nice way to enter two worlds, let's say, at the same time. If you want, you can rewrite this function here in this way, and so now you can recognize what's a shallow neural network with random weights. So it's different from a classical neural network where usually you want to learn the weights. Here they are random, and they are these SJs. But if you want, you can see it at the same time as an element to build kernel methods, an SVM. Because if you take the inner product between the features mapped into points, as m goes to infinity, you recover exactly a kernel. Okay, so now let's start understanding some other ingredients that I talked to you before. So the first ingredients that I said is stochastic gradients instead of gradient descent. So what I'm going to do is that my solution is going to be updated according to the gradient of only 1 point of my empirical problem. So I'm going to take into account only 1 point at each iteration, where these points are picked uniformly at random between my data points. The second ingredient is that I mentioned is mini batching. So instead of taking just 1 point at each iteration, because I don't want to waste, let's say, my GPU's power, I'm going to take a mini batch of B points, and these B points are represented here. So I have the sum of B gradients over B sets of points over B points. And so now you look at this, we're almost done, you look at this iteration here, and the first thing that I want you to notice is that here we don't have anymore the penalization terms getting into the pictures. So there's no regularization term. We are hoping that somehow the choice that I'm making are going to allow me to regularize in an implicit way. So again, if you look at it, the first thing that you may notice and ask yourself is, okay, but what are the free parameters for this algorithm? So I have to choose which step size I take, how big is the batch size that I take, how many random features I want, and for how long I'm going to run my algorithm. And another interesting thing is that I want to pick these parameters here, both to have an efficient algorithm that can scale on a large-scale data, and I also want somehow to see how this plays a role in the generalization properties of my solution. So what I can observe is that the time complexity is in particular MBT, and the space complexity is M. So to get this work a little bit into the pictures, people have studied in the past the statistical properties of a single pass SGD, so where you allow yourself to have T that is at most N, where N is the number of points, which means that I'm going to look at each point only once. People have studied more recently multiple pass stochastic gradient descent, so I allow myself to look at my data more than once. Then again, recently people have studied the effect of sketching, but not in the settings of any iterative methods, in particular not on stochastic gradient descent, but only on ridge regressions problem. So somehow here we are trying to put everything together and see what we can say. And what we observe is that we can control the test error of my iterates against the best possible test error. This again stocking as I showed you before in the first slide, with a quantity that depends on all the three parameters that I'm using. So in particular, the step size, the batch size, the number of iterations, the number of random features. And so now the question that follows is, how can I pick these parameters here in order to have the smallest error possible? And then what's going to happen in terms of computational complexities if I do these choices or not? So there are different options, there are different regimes that I can pick. And remember that what I'm aiming for is to get to this side of the inequality a quantity that is 1 over square root of n. So one possible choice is to say, okay, I'm going to pick, if I want to recover 1 over square root of n, I can pick a number of random features, which is only of the order of square root of n. I can pick a batch size of 1, so I'm forgetting for a second about mini batching. I can pick a step size, which is 1 over square root of n, and then after n iteration, which means 1 pass, so this is vanilla stochastic gradient descent, I can recover my statistical, my desired bound. But then you can say, okay, but here again, I have a mini batch of only 1. If I have a GPU, I would like a bigger one. And then people say, okay, but in practice, you want to pick a step size a little bit bigger because usually it's better because you go faster and you finish before. And it can be seen that another option is to pick, again, in one pass over the data, a number of random features of square root of n, but now we can increase our mini batch to square root of n points, and now we can take a constant step size. So somehow we are happy because we're taking a bigger step size and we're taking bigger batches. And we recover our bound. So now people say, okay, but I was at 1 mini batching, then I got square root of n. Well, what happens if I take it bigger? Because I have more points. I have more computational powers. So what you can see is that if you take a bigger batch size, so let's say that you go up to n, at this point you cannot anymore increase your step size. And right now what happens is that you can see that in order to recover this statistical bound here, I have to go for multiple passes over the data. So I have to look at my data more than once, in particular square root of n times. So, okay, so these are choices. How does this influence the computational complexity of my algorithm? Well, you can immediately, it's easy to see, and we see it later, that this third option is not so good, because basically what's going to happen is that if I have a time complexity of MDT, the previous, the third option just told me that I have to run more times over the data, so I'm spending more in terms of iterations, but I'm just going to increase my computational complexity, and I would like this to be low. But the first two options actually brings the computational complexity down to n square root of n in time and square root of n in space. And these values here are quite good, because are actually a square root of n factor better than both stochastic gradient descent without random features and random features but in a kernel ridge regression setting. So somehow I'm happy, because I've just seen that my algorithmic choices play a role in the regularization and implicitly regularize my solution, so I don't have to put any implicit constraint. And I recovered an algorithm which can be run on millions and millions of data easily on just a single machine. So now let's look at how this works in practice, and let's see if we can observe empirically what theory was suggesting. So we run this data on a high energy physics data, in particular SGD, so these are millions of points. And one thing that we can see is that as the theory was suggesting, we can pick a number of random features which is around square root of n, and picking it bigger, so increasing our computational complexity, doesn't pay us back. So if we pick a bigger number of random features, our classification error doesn't increase more. The second thing that we would like to observe is the story about step size and mini batch size. So this plot here, which may be not the easiest to see from the projector, but what shows you is that it's a classification error on the step size increasing along this x and the batch size increasing along this one. And here, blue is good and yellow is bad. So one thing that we can observe is that there's somehow a regime that tells us that we can increase the step size and at the same time increasing the batch size, and we're going to have the lowest classification error. But after some point, which is around square root of n of batch size, we cannot anymore increase batch size and step size and recover the same deep blue that we can observe below that threshold. Why this? Well, because this plot here is for a fixed number of iterations. In particular, this is after one pass over the data. So you may ask, so that means that for bigger batch size, I cannot recover the same good, the same good 20% classification error? No, actually you can, but you have to run your algorithm more. So somehow there's this threshold of magic mini batch size of square root of n that tells us that there's a mini batch size that's better to use with respect to others. And so summing up what you've shown here is that the number of passes, the step size, mini batch size, sketching, and number of iterations all controls the test error, all controls the statistical properties of my solution. And this because somehow they introduced a bias in my function, and also we can actually run this algorithm here on large amount of data. We can also see that if we go for further and more refined assumptions, we can recover even faster rates. So we can go a little bit faster, theoretically speaking, and also we studied another regime that I didn't show you here, where we allow ourselves to have a step size that decrease. But long story short, we cannot, we don't improve, and we recover more or less of the properties that I've already told you. And from here on, future work, future idea is to try to go for beyond least square penalization. Instead here the problem that we formulate was a least squares problem, and try to see other ingredients in optimization, how they influence our solution, as parallelization is another thing that we're interested to study right now. And then from here to the big world of non-convex problem. Yeah, and this is it. Thanks for your attention.
Questions?
Yes, can you please go back to the empirical results slide? So, what is the number of random features chosen for the plot on the right side? Is it
This one?
root of n?
Yes, I think so. I don't remember particularly, but we tried. I don't remember for this plot here, but we tried for many, and
it's
they
more or
don't.
less the same thing.
Yeah, it's more or less always the same thing. I mean, still according to, so yeah. So it was at least square root of n. So we didn't want to try to see what happens if you are around here and,
Okay.
and then you look there.
Okay, so in the other way around, which is the batch size and the step size for the other experiment?
Again, I don't remember for this one specifically,
Yeah.
but we tried multiple, and we didn't observe any influence in the batch size of how the classification error decreased as we varied the number of random features.
So if you have to make a suggestion of a reasonable policy to find the best parameters for a problem, what would you suggest?
Sorry, say it again. The
If
best
you-
parameter for?
For some problem,
Mhm.
you have to pick the, I mean, okay, I can use square root of n, but you suggest to just stick to square root of n, or
No.
do some
No.
research around?
Do some, yeah. So first thing first is that these are theoretical results for this problem, for this least squares problem, and so you have to pick the two things in a different way, when you study something theoretically and when you study something empirically, practically. So, so here, again, we simulate the same problem, and what we see is that theory is right. Here, theory is right. So this may not be the best choice to pick exactly square root of n, but you know that around there, that's a reasonable choice. And same thing for the number of random features. So what you can do is that instead of starting to do cross-validation at random for your algorithm, you can start from theory and say, okay, so theory suggests me that I can stay around here with number of random features, so I'm going to check if from there above I still decrease or not. And for batch size and step size, you can do more or less the same thing. Plus, you know that usually increasing step size allows you to increase batch size. But what you also can observe here is that after a while, increasing batch size it's not going to be allowed anymore, increasing the step size. So you know that there is some optimal choice. And what else can I suggest you? Yeah.
The other thing is what is the intuition? It's something on the beginning which I didn't know. What is the intuition behind random features? I mean, why do they work in the first place?
So
it's not clear to me how do they transform the data. So yeah, that's one.
So basically, the point here is that you are somehow looking at the spectrum of the Fourier spectrum of so depending on which nonlinear function and which probability distribution you use to sample your random vectors, you are somehow projecting your points into other spaces that you can somehow see as you move to you are playing in another in a Fourier space. Okay, so what you can see is that if you pick in particular Gaussian distribution and the sigma, which is a cosine function plus 2 times pi of uniform distribution F, you can recover what are called random Fourier features, and so this is somehow the intuition that I can give you. But if you're interested
so
more,
the number of random features is somehow linked to the number of harmonics.
Exactly. So how many sampling of that you are taking, and if you're interested to see how where they come from, so they come from a series of works of Rahimi and Trecht, the first one in 2006, and there they study in particular the translation invariance random Fourier features.
Okay. Thanks. Other question? I have one. So you're studying the problem in a very specific case, right? You have the least square and you are kind of approximating like you're doing the optimization procedure because you want an L2 regularization handling, right?
So I'm not allowed. I'm not imposing any L2 regularization. So this is the thing. Usually, you study an empirical problem with an L2 regularization.
Yes, and you say I do this procedure and I'm hoping to get some water regularization.
Yeah, because what I do is that I try to minimize this functional here without this.
Yes.
I delete it.
And okay, so my question is, does it work if you impose? So your regularization is kind of preventing overfitting, right?
Yes, having low, what is called excess risks, which is this quantity here.
So would these guidelines work if I'm imposing a regularization that is imposition of prior knowledge rather than preventing from overfitting? So if my function contains some prior knowledge.
So I'm thinking. It should be, but what will be able to say. So you are still gonna be able just to control this quantity here. So you cannot. You don't know how the. So yeah, you're still gonna recover. Let's call this a generalization bound. But you don't have to impose any L2, and you can impose others. At this point, the iterates are gonna change. So here is gonna pop out another penalization term inside this gradient, and I don't know. I mean, it would be interesting because probably at that point, if you want, here's gonna pop out as well some relation, some trade-off with the regularization term of your extra penalization.
But you can kind of use it to say probably it works even if I use it for another.
Yes, unless if it satisfies some assumptions, so you don't go to non-convexity, you don't do
It's differentiable.
yeah, this kind of thing, and then you can.
So if you use proximal methods, it's just in a completely different.
Yeah, you have to do another analysis.
Other questions? Okay, so that's the thanks. Thank the speaker again.